Hello learners. In my previous videos we have already discussed in detail about different type of coordinate systems. We have seen rectangular coordinate system, cylindrical coordinate system and spherical coordinate system. We have also covered the way to identify shapes in these type of coordinate systems. Hope you have seen those videos. I'll provide the link on the description. In this video, let us start with the conversion of one coordinate system into another. In electromagnetic theory, you will face the problems in which you will have to either convert one coordinate into another coordinate before solving the problem, or after solving the problem, before getting the answer, you will have to convert into the desired coordinate system. You have to convert the three coordinate systems into one another. Mostly you will face the problems where you have to convert the rectangular coordinate system into another coordinate system or vice versa. Here it is shown in the first 2 points. One is where the Cartesian or the rectangular coordinate system is given and you have to convert it into cylindrical coordinate system or vice versa. And the second is when you have to convert the spherical coordinate system into rectangular coordinate system and vice versa. And there are rare cases where you will see the conversion of cylindrical coordinate system into spherical coordinate system, but if you know these two methods, you will definitely be able to solve the last one. Let us start with the first type of conversion. This conversion is from Cartesian coordinate system to cylindrical coordinate system. So you will be given a point which will be in XYZ and you have to finally bring it to rho phi Z. We have already seen these two type of coordinate systems. When you will convert from one coordinate system to another, you have to imagine the Cartesian coordinate system and the cylindrical coordinate system and their dimensions on the same diagram. So here in this diagram that you see on the screen, in Cartesian coordinate system, you know that our basis is the axis x, y and the axis z. Any dimension that is parallel to x-axis is known as x dimension. Any dimension that is parallel to y-axis on the xy plane, that will be known as the y dimension. And any dimension that is parallel to this vertical z plane will be known as the z dimension. Now our task is to convert this xyz into rho phi z. Now let us again bring cylindrical coordinate system and their dimensions into picture. Do you remember that in cylindrical coordinate system there was a dimension known as rho, and that was the radius of the cylinder. And we had a dimension known as phi. Phi was the azimuthal rotation which enabled us to rotate the cylinder into completely 160 degree. And there was a dimension known as z. This z is same as what z denotes in the Cartesian coordinate system. So to convert xyz into rho phi z, let us first see and concentrate on the xy plane. So let us concentrate on the triangle OAB. In this triangle OAB, AB is perpendicular to OA because AB is the perpendicular which is dropped on the x-axis. So in the triangle OAB, if you apply Pythagoras theorem, you will see that rho is the hypotenuse, x is the base and y is the perpendicular. So to find out rho, we have to do nothing but find out perpendicular square plus base square. This is nothing but Pythagoras theorem, right? So to find out in a right angle triangle, I'll draw this vertically. In a right angle triangle which has O, A and B as their vertices, and we know that this OA dimension is x, OB dimension is y, and AB dimension is rho. I have drawn this triangle. This triangle has rho as one of the dimensions, which is hypotenuse, and x and y's are bases and perpendicular respectively. So to find out rho, you have to apply this Pythagoras theorem. So it is written here, as you can see. And also in the same triangle, we know that this angle is phi. See, this phi corresponds to this phi. So if you have an angle phi in a right angle triangle, to find phi, it is very simple. We have to do tan inverse of perpendicular upon base. That means y divided by x. See, you have the perpendicular y and you have the base x, and you know that tan phi is perpendicular upon base. So we have two dimensions present here. One is the hypotenuse, which is rho, and rho, as you know, it is the radius of the cylinder. So if you want to convert the rho into x and y coordinates, you have to find out the square root of x square plus y square. And phi, which was the azimuth of the cylindrical coordinate system, to convert it into x and y, we have taken this triangle and we have found out tan of this phi, which is y by x. So we have rho, we have phi in the form of Cartesian coordinate system, and what is left? This z is left. And as I have already told you that the z in the Cartesian coordinate system is the same as the z in the cylindrical coordinate system. So here we don't need to convert it, it will denote the same thing. So that is how we'll convert anything that is given in the Cartesian coordinate system into cylindrical coordinate system. Now what to do if you want to convert the vice versa? If you want to convert now the things which are given in cylindrical coordinate system into Cartesian coordinate system, what will you do? It is very simple. You have to draw the same diagram, follow the same rules, even you have to see and concentrate on the same triangle. In this triangle OAB, let me draw it again vertically. We have AB as y and we have a vertex O. So OA is x and we have this rho as the hypotenuse. So x is base, as you have already seen, y is perpendicular. So, and also this phi is the angle between OB and OA. So because we have to this time convert things into rho phi z, we have to follow a different approach but the same triangle. Let us see, we have seen tan phi, right? So cos phi and sin phi are left. We have to use this cos phi and sin phi while evaluating converting things from cylindrical to Cartesian coordinate system. In the triangle OAB, cos phi is, cos is base upon hypotenuse. And what is base here? Base is x and hypotenuse is rho, and sin phi is perpendicular upon hypotenuse, and perpendicular here is y and hypotenuse is again rho. So if you notice these two expressions, we see that on the right hand side we have x, and in the whole expression we have only x here as in the Cartesian coordinate system and y in the Cartesian coordinate system in the lower expression. So can we do this x is equals to rho cos phi, and can we do this y is equals to rho sin phi? Yes, we can very much do this. And these two expressions, this solves our problem. So the left hand side is x phi, right hand side is rho phi in some trigonometrical expression, and we know that this trigonometrical expression is correct. So we can say that we have converted the cylindrical coordinate system into Cartesian coordinate system, but only two coordinates are covered here. What to do with this z? and z is, as I have already told you, it is same, so we don't need to convert z. In Cartesian to cylindrical coordinate system and vice versa, z is not converted, z will be kept same in both the coordinate system. So this is how you will convert anything which is given into cylindrical coordinate system and convert it in, you have to convert it into Cartesian coordinate system. This is how you will do it. Now let us see how to convert Cartesian coordinate system into spherical coordinate system. We have already seen all the things, all the dimensions that are present in the cylindrical coordinate system. There are two new dimensions which are present in the spherical coordinate system. One is r and one is theta. Phi is same what it was in the cylindrical coordinate system, and Cartesian coordinate system we are always familiar with it. It is x, y, z. So let us again recall what are the things, what are the dimensions which are present in the spherical coordinate system. A spherical coordinate system had a radius which comes out of the origin, and this radius was the radius of a sphere. The sphere which was only considered 1/8 of its part. So this r was the radius of the sphere, and this radius line, this r, it was making an angle with the z axis on the vertical plane. So we called this angle as theta. So other than phi, we have now a radius r and the polar angle theta. And in this diagram, this vertical angle, these angle theta and r, is shown with a new triangle. This triangle is right angle triangle OPC. In this triangle, you should always remember that this angle is 90 degree. So let me draw this OPC vertically. In this three-dimensional form, it is difficult to imagine that PC and OC are perpendicular to each other. So let us say that this is PC and C is the point on the z-axis, which we are saying is right angled point. So PC and this is O, and this O is having this angle theta. So what I have done, I have made this triangle OPC vertically so that you can easily imagine that this r is the hypotenuse, PC is rho, and OC is z. I have mapped all the sides of this OPC triangle vertically, and our familiar OAB will remain same. This lower triangle OAB is same. It has hypotenuse as rho, perpendicular as y, and base as x. X was having the dimension O and A, and this was B. So this triangle and their dimensions will not change. The new introduction we have to concentrate on. So let us see that if we want to represent theta in the form of let's say tan. Tan is the trigonometrical identity, right? So can we write theta is equals to tan inverse of rho by z? Yes, with this triangle OPC we can definitely write this. Okay, so theta is equals to tan inverse of rho by z, but we know that we cannot write rho because our final result should be in the form of x by z. But do you remember in just previous slide we have seen that rho can be written as under root of x square plus y square, because the lower triangle helps us do that. See, rho can be written as x square plus y square because this lower triangle is also following Pythagoras theorem and it is also a right angle triangle, right? So theta can be written as tan inverse of under root of x square plus y square divided by z. Let us look at this triangle again, triangle OPC. We can say that r, which is the hypotenuse, can be written as under root of rho square plus z square, because rho is the perpendicular and z is the base. But again, in this conversion we cannot write rho, but we know that rho can be written as x square plus y square, means rho square can be written as x square plus y square. So this r finally becomes under root of x square plus y square plus z square. So we have converted theta into xy, we have converted r into xy, we are left with phi. Phi is simple. Phi can be converted using this lower triangle. This lower triangle tells us that we can write phi as tan inverse y by x. Yes, this is similar formula. This is similar formula that what we have seen in the cylindrical coordinate system. As I have already told you, the meaning of phi will not change. It will remain same as the cylindrical coordinate system. So we have converted theta, r and phi into xyz coordinate system from r theta phi coordinate system. While converting from spherical to Cartesian coordinate system, the previous diagram will not change because the things are same, and we will again have the triangle OAB, which had base as x, perpendicular as y, and rho as the hypotenuse, and this was the angle phi in this right angle triangle OAB. And also this vertical right angle triangle will be considered. This is theta, and this corner was O, and this is P. So PC is rho, this base is Z, and we have the hypotenuse as R. Let us first concentrate on this triangle. In this triangle, what can we write rho as? See, rho is perpendicular, and rho can be written as r sin theta. Why? Because rho is at the perpendicular, and we know that sine is perpendicular upon hypotenuse. So because sin theta is equals to rho by r, we can write that rho is equals to r sin theta. Also z, can we write z as r cos theta? Yes, we can write it because z is the base. So cos theta is equals to base divided by hypotenuse. So z can be written as r cos theta. So as you can see, while writing z is equals to r cos theta, we have converted z into spherical coordinate system. So this is one of our answers. If you are given with, if you are provided with r, theta and phi, you can directly find out z by finding out r cos theta. Also, let us see x. We know that x was written as, in using this lower triangle, x can be written as rho cos phi. But we know rho is this, rho is r sin theta. So we can write r sin theta cos phi. We have just substituted the value of rho here in front of x. Also y, we remember from the cylindrical convergence, cylindrical coordinate system conversion, y can be written as rho sin phi. And again, we cannot write rho in the right hand side because cylindrical coordinate system should not come into picture here. So we can write rho as r sin theta, and finally this y becomes r sin theta sin phi. So without even knowing it, we have converted this z, we have converted already, x we have written in the form of spherical coordinate system, and y also in the form of r theta phi. So our aim is now done. What we have planned, right hand side should be in the form of r theta phi, it is there, and left hand side should be in the form of xyz. So this is how you will convert the spherical coordinate system into Cartesian coordinate system. In the previous slide and in this one, you have seen that we have taken the help of two triangles, and both of these triangles are right angle triangle. One is on the base and we called it triangle OAB. This OAB triangle is on the base, and we have seen it previously. This is the same as the triangle OAB, and another triangle which is vertical, in which the right angle side is corner is this one with the C vertex, and this triangle is OCP or OPC, whatever you want to call it, but it had a right angle and an acute angle which was known as theta. This theta is our polar angle. So this is how you will convert one coordinate system into another coordinate system. Spherical coordinate system formula are, some people say that they are tough, but you have seen that it can be done in two parts. If you know the conversion from cylindrical to Cartesian coordinate system and vice versa, you will know this expression, and if you know this expression, these three answers will be very simple. Now let us see the last conversion. If in case you want to convert rho phi z into r theta phi, rho phi z into r theta phi, we have done it. Unknowingly we have done it already. See, you know that rho square can be written as x square plus y square. So while converting from spherical coordinate system into rectangular coordinate system, we have done this step. Do you remember this step? If you don't use this middle step, if you directly convert r into this rho square plus z square under root, you have seen that this right hand side is cylindrical coordinate system and the left hand side is spherical coordinate system. So see, we have converted. Unknowingly we have converted. So if you have theta on the left hand side, and if you have all the coordinate system as rho phi z, see, this rho and z are helping us to convert theta. So while converting from cylindrical coordinate system to spherical coordinate system, it is simple. You have to follow the intermediate step that we have used. This rho will be kept as rho, not as x square plus y square, like we did in the previous two slides. And here also we know that rho can be written as r sin theta and z can be written as r cos theta. So you can see this right hand side is spherical coordinate system. All the dimensions here are spherical coordinates, and rho and z they belong to cylindrical coordinates. So phi represents the same thing, so we need not to worry about it. So I hope that with this presentation you have understood that how to convert any coordinate system into any coordinate system. You will need it while converting the vectors also from one coordinate system to another coordinate system. So tell me in the comment section if you don't understand anything. So thank you, happy learning.